we can get started. So welcome everyone to the One World Combinatorics Onwards seminar. Our speaker today is Michael Baake from the University of Bielefeld, and he's going to speak to us about hats, caps, and specters.
Yeah, thanks a lot. Thanks for the invitation and the opportunity to talk about this here. So can everyone see the slides and hear me clearly?
Yes.
Good. Okay, so this is to a large part joint work with Franz Gähler, also from Bielefeld, and Lorenzo Sedun from Austin in Texas, and there are a few bits and pieces in between where other people have contributed. And my menu is this. I have to click that away. Okay. I will briefly talk about the hat, and you see my cookie version of it, which we made. You've all done that, I'm sure, yeah, with some of these downloadable 3D printing files where you can make your little form. And then I will spend a bit of time why perhaps one should care about this example outside the obvious geometric attraction that it has. And then I will talk a little bit about shape changes and how you use that to actually ask and answer the question, what is the long-range order of the hat tiling? So this talk is not about how it came about or how you prove aperiodicity. That has been marvelously done by the originators of the discovery. But this is really a talk about what is actually the structure of it. And a big role will be played by what I call the cap tiling. And the cap is obviously referring to a base cap, but it has some other meaning that I will explain. And then I will make a link to Meyer's theory of model sets and actually show that we can get a connection to a projection object. And we'll go back to the hat. And then, if time permits, I'll actually speak a little bit about the spectre, which is a monotile in a more stricter sense than the hat. Okay, and why is that so? Because what is going on here? All right, here we are. Here is a picture of a part of the tiling, and I saw it on a fridge just a few minutes ago. A patch of the tiling of hats and anti-hats, the anti-hats in gray. And because of that you need the tiles and the reflected version, it's a matter of taste whether you want to call this monotile or not. And the spectre, which we will touch later, is one that only occurs in one orientation. Okay, now the thing here is that tilings of the plane are possible, but only aperiodic tilings. You all know that. You have seen that in many talks and videos, I'm sure. But one special feature that is different to previous ones is A, that it is a purely geometric form, but B, that it also breaks a certain symmetry. And you see it clearly here. The hats are much more frequent than the anti-hats. So you actually have two types of tilings, namely one tiling where the hats dominate and one tiling where the anti-hats dominate. Yeah, so in that sense, there's also a slight difference to previous versions. Okay, what are predecessors that are worth mentioning? We have all seen to the upper left, the two rhombi with the decoration that give rise to the Penrose tiling. That, of course, is not a monotile because we need two. But there is an almost monotile version that often gets forgotten in this context, namely the Gummelt cluster, which is the decagon to the lower left. This is sort of say a monotile type solution to the dual problem, not the tiling problem, but the covering problem. Yeah, so there is this decagon and certain rules how it can touch each other and overlap, and then it covers the plane only non-periodically, and actually the set of Gummelt coverings of the anti-Euclidean plane is equivalent to the Penrose tilings, and it was deliberately looked for and then found by a group in Greifswald, initiated by Christoph Band, who had the idea that the Penrose tiling is so close to the idea of a monotile that one should look for this version, and at least the Gummeldecagon gives a solution to the covering of the plane with one object, not yet the tiling. Roger Penrose made his own attempt with a thing on the upper right, which he calls the 1 plus epsilon squared tiling. So the 1 is the hexagon, and the epsilon is the line object. Yeah, so this little thing that looks like a boundary with these little decorations, and the epsilon squared tile, which is the cornerstone at the edges, and he could show that this forces aperiodicity, but it's not quite a monotile. And but at least it was an explicit attempt to construct one. And before the hat and the spectre, the best solution then was the Sokola-Taylor tile, which is to the lower on the right, lower right. It's a hexagon with some decorations, and you have to observe certain rules like continuing lines and matching points of next to nearest neighbor objects as indicated by the double arrow. And you can replace this by a purely geometric tile that is connected, but it's not simply connected. So even though this does force aperiodicity and it does define a unique Li class, it cannot be represented by a disk-like tile alone. Yeah, so you have cut points if you realize it geometrically. And then the head and the spectre came about, and everything changed. And still, to many, this looked like a kind of a curiosity. One had found it, okay, but why care? And I want to offer you a few thoughts of why it's actually more than a geometric discovery. I dropped the point that it's lots of fun to play with it. We had that a year ago at Headfest in Oxford, and entire classes of pupils came and had big fun of laying big head tilings on the floor. And there are lots of records you find in them on the internet. And it's clearly the first purely geometric monotile that is disk-like, sure. But what is the importance beyond that? So the first thing I would like to mention is that clearly there are connections to dense sphere packings. And you know that there's a lot of advancement in sphere packings lately, but that on the other hand, we still know very sphere packings in higher dimensions. I mean, except 8 and 24, yeah, and maybe 2 and 3. But in particular, we also know that there are some dimensions where the densest sphere packings aren't periodic, yeah. So there are lots of issues, and that brings me to the crystallization problem. If we have a single tile that tiles the plane only aperiodically, then we could in principle imagine a situation where we consider this object as a particle and we prescribe a potential that basically is a hardcore potential that tells you if you put two pieces together, you pay a price if they don't match, and you pay a price if they overlap. And then you look for the minimum energy configurations, and they will just be all these tilings. Yeah. And if the ground state is I say ground state, if so to say the minimal energy configuration is non-periodic, yeah, then this sheds a bit of water on the conjecture that you would always expect the minimal configurations to be periodic. Yeah, and this is a big open problem in mathematical physics, to prove that given a particle and some potential, single particle and some potential, is the minimum energy configuration necessarily periodic? No one can prove it, yeah, so far, and maybe it isn't true, yeah. Maybe I drop the other things because the other points will automatically come as we go on, except for the last. This example and also the recent progress on tiles in higher dimensions, higher really meaning very high dimensions, do raise the question how well we actually understand Euclidean space if the dimension increases. Yeah, so our intuition is pretty much built from 2 and 3 dimensions, and maybe a little bit of 4, but how it looks in 17 or in 113,000 dimensions, that is pretty unclear. And that is why all these examples are really important. Okay, now, the head family of tilings. Let me see whether I can actually also. No, I can't see that at the same time. So if you have any questions, you have to interrupt me, because for some funny reason, I can't see the chat at the same time on my screen. There are many head-like tilings. Yeah. As for the head tiling itself, the important step in proving all this was the realization that if you start to build them, inevitably they combine into clusters, and these clusters have a local structure that led to the identification of certain metatiles. And then you can study the metatiles and find that there is a combinatorial inflation that induces a hierarchical structure. And then you also realize that there are many deformations possible without changing the local combinatorial structure. And I will look into that in a little more detail in a second. And that gives rise to this family of monotiles. The hats and the turtles are maybe the best known, but there is a one parameter family of other things that do. And now the questions that I want to address from now on are the following. What is the overall structure of such tilings? Yeah, as a tiling of Euclidean space, the Euclidean plane. And I will ask the question, is there Bragg diffraction? So if you would sort of say, consider this as your object and you do a scattering experiment to detect long-range order, would it be so? And would actually maybe you would only see peaks if you do that? Yeah. And if so, could it be that it's actually a projection tiling like the Penrose tiling? And therefore, at the end, you could ask the question, is the long-range order so perfect that these structures are actually quasi-periodic? And the rest of the talk is my attempt to give you the answers to these questions. And as a spoiler, I will tell you that the answers are yes, 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 and yes. Yeah. So, how can we see that? Now, here is again a little picture that I'm sure most of you have seen, namely how you overlay the meta tiles onto a head tiling. And you see that around an anti-head, I've done it here for a head-dominated version. Around an anti-head, you have these irregular hexagons, and then there are also little triangles with 2 orange and 1 blue edge, and parallelograms, and some dented parallelograms that always comes in triples and look like a threefold windmill structure. Yeah, and those are the 4 meta tiles with which you can perform your entire analysis if you want. And now I'm asking the question, what can we do in terms of shape changes? And what's a shape change? Well, a shape change is a map F from classes of edges into R2. So the easiest shape change that you could make would be you take your head tiling and you double the length of every edge. Yeah, that way you just replace the head by a bigger head. Of course, that gives you the tiling on a different scale and nothing much happens otherwise. But there are many more possibilities of shape changes, and we are interested in the ones that are closed if you sum the changes along the edges of a tile. So if we sum over all edges that are at the boundary of a tile, and we sum this f of e, each f of e is a vector in R2, that should give 0, because if it doesn't, then you would make a shape change that turns the tile into something different. In particular, it's no longer a tile because it would be open or whatever. Yeah, so that's That's a requirement we need to have. And then, of course, some shape changes would just induce MLD transformations, where MLD stands for mutually locally derivable from one another. That is, some shape changes would just mean you can write down a local rule how to redraw your little hat into a different shape, and you do that everywhere, and then you have your new tiling and vice versa. And these two things, they are kind of trivial, because if you can, by a strictly local rule, redraw one into another Escher-like, let's say, then it's clear you should consider those as two representations of the same kind of thing. And therefore, we are interested in shape changes modulo such local redrawings that are strictly local. Yeah? And here is an important result that goes back to Alex Clark in London and Lorenzo Sadun in Austin, Texas. And they have proved a couple of years ago that shape changes modulo MLD transformations, they have a nice moduli space, and this moduli space comes about as the first check cohomology of the tiling space with the coefficients in R2, where this is really, so to say, a bit of abstract math entering here. The topologists like it a lot. Other people say, what the heck is a check cohomology? And I'm not able to explain that here in a second. But the point is the following. The tiling space X that we have, that is the space of all tilings that we can have. And in particular, if we have one head tiling, we can also consider all translates of a head tiling and then take a closure in the obvious way to compare two tilings, where we say that two tilings are epsilon close if they agree on a ball of radius 1 over epsilon exactly. And that turns the set of all these tilings into a compact space, X, and that is the tiling space of the tiling. And this tiling space has an interesting structure because it's an inverse limit. You could actually describe it by sort of say, first saying how it looks on the level of the tile, then at the level of the 1 corona, then at the level of the 2 corona, and ever so on. And this way define your tiling space as an inverse limit, where you prescribe it on larger and larger patches, ultimately describing the tiling space. And it's a known result from algebraic topology that for such spaces, the cohomology, the check cohomology is actually computable and turns into a direct limit of the cohomology groups of finite cell complexes. And the finite cell complexes, they just come from these prescriptions, how you close it by saying who is a neighbor of whom. And now we have this combinatorial inflation structure that actually tells us that in this direct limit structure, it stabilizes, so we can actually compute this thing. And that is what, so to say, starts at the analysis of this tiling space. Yeah. So, and what types of shape changes, or if you want, cohomology classes, do we have? First of all, we have linear maps. For instance, we could scale the entire tiling. Yeah? Like I said before, we could replace every edge by an edge twice the length. Here we would just replace the hat by a bigger hat. That change is essential, but we know what it does. It's just a rescaling, so we have everything under control. Or we could have a rotation. Yeah? So we could replace every edge by a rotated version so that it still adds up. What would that do? It's still essential, but it rotates the entire head tiling, say by pi, yeah? And that's also well understood, so that's not interesting. And then there's another class, it's the class of asymptotically negligible shape changes. That are shape changes that we can make, and they are not shape changes that I can locally redraw, but if I sort of say, look at the effect at longer and longer distances, it gets irrelevant, yeah? So we change something, and we change the shape, and we change the position of the tiles, maybe effectively by all these shape changes. But if I'm far enough away, I don't notice that anymore, and in the limit it goes to 0. They are asymptotically negligible, and they are interesting but still controllable. And then there are other shape changes, namely essential shape changes that change the long-range order, but they are absent for the head family of tiling. So that's the first result that we have proved in this paper, namely the head tiling possesses no non-trivial asymptotically relevant shape changes, and the asymptotically negligible ones, they lead to topologically conjugate dynamic systems. So in other words, all members of the head family of tilings, because they come about by such shape changes, they share their essential topological and spectral features. Yeah. So all these things from the turtles and so on, they are different tilings, but as tiling spaces, they are topologically conjugate. And if we understand one, we understand them all. Yeah. But note, it's not a local rule in general. Yeah. So this is different to symbolic dynamics, where you are used to the Curtis-Linden-Hedlund theorem, yeah, telling you that all these modifications, these homomorphisms that you can do, they are all described by block maps with a finite radius. So the corresponding thing of block maps with finite radius, these are the MLD transformations. But topological conjugacy is more than that. Yeah. So what I'm saying is there are lots of tilings that only asymptotically, yeah, have the same order, but they are not obtained from one another by one of these MLD transformations, aka geometric block maps. Okay. Now, another advantage of this analysis is that now that we know all the originally described and even more tilings are in the same topological conjugacy class, we can actually look for an eigenvector of the cohomology matrix by Perron-Frobenius. In this case, there's just one eigenvector, and that's a very specific shape change. And if we use that, we can choose an example in this topological conjugacy class that is self-similar. Yeah, the original head tiling is not self-similar. It has a combinatorial substitution rule, but not a geometric one. And here is the image for the cap tiling. This comes about by doing a shape change that we are now self-similar. And you can still see there are these hexagons. They look a little different now. There are the triangles, and there are the parallelograms. They look shorter now, and we still have the windmill type structures, but they are all a bit different. But this is now self-similar. And now we have the advantage of having a geometric inflation. And on the next image, I show that one. So we can now do the following. We can blow it up by the inflation factor, as the power of the golden ratio, and then replace it by a suitable collection of tiles of the original size. And it is not a stone inflation, as you can see, because the inflated tiles, so to say, the level 1 super tiles, that are the ones with the fat lines, yeah, they are replaced by a collection of shaded tiles, and that's done in such a way that if you do this, it is consistent. So if you iterate it that way, you fill the plane by this inflation rule without gaps and overlaps. Yeah, so it's a perfectly sane inflation rule. But it's not a stone inflation. So if you if you would insist on a stone inflation, you would have to do the typical fractalization dance and replace the tiles by fractals. But there's no need to do that. And what is also shown in this picture is a collection of white tiles of the original size. Yeah. So the inflation step consists of blowing everything up by the inflation factor and replacing each tile by the shaded tiles, and that would give you the tile on the original scale. But all the white ones are also forced. So that actually means that in this inflation procedure, we do not only have the tiles that we have to use, but we also know what the possible neighboring tiles must be. There's no freedom. or for those who know that, in other terms, this is the only possibility. This actually proves that this inflation rule forces the border. Yeah, and that makes various calculations, in particular the calculation around cohomology and so on, makes it a lot easier. But that's a technicality. Now, the spectrum of the cap tiling. That's the cap tiling is the self-similar member of this topological conjugacy class. Yeah, that comes about as follows. So the cap tiling also defines a dynamical system very much the same way. You take one cap tiling, you take the orbit closure of its translates under R2. That gives a compact space X. And under the translation action of R2, this is strictly ergodic. The spectrum is pure point and all eigenfunctions are continuous. So we have topological pure point spectrum. And the same applies to all tilings from the topological conjugacy class, because this is preserved under topological conjugacy. Yeah. So this is the first theorem that really tells us the long-range order of this monotile tiling is exceptionally nice. Yeah, it's not something that kind of, at least I don't know any general principle that would guarantee this. Yeah, so I see no principal reason why a monotile should have pure point spectrum. Now, how do you prove that? Well, you have it described as an inflation tiling, and there is an overlap algorithm due to Solomiak, which you can program, and you can just let it run, and then the program prints you on the screen, yes, and you are done. And strict ergodicity of the system and continuity of eigenfunctions, that follows from the fact that this is just a primitive inflation tiling. Yeah, so that part is actually easy. And the first part, well, it gives you yes, but it leaves you with a feeling, okay, I mean, did I program it right and so on? But yeah, okay, apparently it is yes. And you might say, okay, maybe that's what I expected because the inflation factor is a Piso-Vijaya-Raghavan number, but still, this gives no real insight. And but it's a good first step to make sure you're on the right track. Yeah. So what what can we now do? Now is the point where we can make the connection with the work of Yves Meyer. And how do we do that? Well, we replace each of these tiles of the cap tiling by a control point, keeping a certain color. And on the left, you see the 4 tiles with a corresponding control point, orange, blue, green, and purple. And the control point needn't be a vertex point. It needn't be inside the tile. The only requirement is that drawing the control point must be doable by a local rule, an MLD rule. Yeah. So in other words, if I have one of these cap tilings, I know exactly where the colored points are, and you can convince yourself that this is the case by just making up your little rule. And you see all the points are inside the hexagons, and they are always at specific positions of the hexagons, and which color it is depends on the neighboring tile. So that's a local rule, that's clear. And then you also have to show the opposite, namely, if you would be given such a point set, so erase all the lines, can you redraw all the lines? And that, again, the answer is yes, because you know that the 3 points are always inside one of these hexagons, so you know where the hexagons are. And then there are always configurations where 3 hexagons are arranged around a central triangle, and you can identify those, and from there on you can color the points and reconstruct all the tiles. So the tiling and the colored points, they are MLD as pattern structures. Okay, and now the point is that for point sets, we have this nice theorem, which is in Meyer's original book from 1972 and was later on rediscovered and rewritten by Robert Moody in the late 1990s. And that basically says that if everything is set up in such a way that you can understand your points as a projection of lattice points in a higher dimension with some restrictions, then the point set that you get that way is a cut and project set with nice properties, and it has pure point spectrum. So first you prove that it actually has pure point diffraction spectrum. I explain that in a second. And then by a well-known equivalence theorem, we know that pure point diffraction spectrum and pure point dynamical spectrum are equivalent. So that can be done. Maybe the details are not important here, but let me just remind you where the term diffraction spectrum comes from, because that's something that's not so well known in mathematics. So it's really coming from this little optical experiment. Yeah. So we have a little laser, and a few weeks back in Lumini, I actually demonstrated that this is real. You can really do this experiment. You widen the beam, and then where you have the green slab, that's your obstacle. Say your head tiling is on a slide, and then you shine the laser light through it, and then you look what you see on the screen. And on the screen, you see the absolute value square of the Fourier transform of the function that describes your tiling, your obstacle. Yeah, so your 0, 1 function for where it is a line and where it's not a line. And that is an image with sharp reflexes. And here is an example how this would look if you would do that for the Ammann-Benker tiling, which is an 8-fold symmetric relative of the Penrose tiling. I'm sure most of you have seen that as well. So that's a tiling of the plane with squares and 45-degree rhombi. And that can be described as the projection of a 4-dimensional lattice into an irrational oriented plane that is invariant under 8-fold rotations. And if you calculate it, then you get the image to the right, and that is indeed the diffraction image that you would see on the screen. And the dynamical spectrum is the support of this object. Yeah. So each little circle means a sharp spot on your screen, and the precise position of the spot is the center of the circle of the disk, and the areas corresponds to the brightness of that peak. Yeah, and the dynamical spectrum is just the set of all these locations. Yeah, so that's how you use the Meyer approach to make this spectrum visible and prove it. Okay, and now you can do the same for the cap tiling, or more precisely, for the control point set of the cap tiling. So first you identify the return vectors. So you calculate what are the vectors that move configurations to translated copies of the configurations, and they span a certain module, and this module has rank 4 over the integers. So it comes from the projection of a 4-dimensional lattice into a certain direction. You can identify all that, and then you can lift all your points into internal space, and according to the 4 different colors for the 4 types of points, they fill this funny object. Yeah, so overall it's a hexagon, and the purple points, they fill these triangular shapes, and the other 3 types of points, they fill these shapes that have partially straight boundaries and partially fractal boundaries, which you can easily compute by a Koch curve type construction if you want. Yeah. So first of all, this now explains the name of cap, because it refers to the base cap, but it's also the abbreviation for cut and project. Yeah. So the cap tiling, that is, to recall, that is the self-similar member in the topological conjugacy class of the head tiling. Yeah? This guy is a projection tiling, and strictly speaking, I have actually only shown that there is a cut and project set that is a superset of what I have, and we now still have to show that actually it's the same set, and that is done by calculating the density of the points in 2 different ways. So one is, there is 1 control point per tile. So if you know the area of the tiles times their frequencies, you can calculate the density of the points. And that's an exercise in Perron-Frobenius theory, playing with the inflation rule. Yeah, it's self-similar, so you can use the Perron-Frobenius eigenvector to calculate that, and the shapes of the tiles you can also calculate. Yeah, and the other way to calculate it is, you know that the density of a cut and project set of this type is given by by the area of the window, which is just this hexagon, which you can easily calculate, times the density of the embedding lattice, and that gives the same number if you work it out. Yeah, and that means we have actually shown that our set lambda up to a null set is the same as the cut and project set, and the null set doesn't enter the diffraction. Yeah, so we know it has pure point diffraction. And by the general correspondence theorem, we know it has pure point dynamical spectrum. And because it's a primitive inflation system, we already knew that the eigenfunctions are continuous. So we have topological pure point spectrum. Yeah. And now at least we see a geometric reason that I think gives a little more insight than the overlap algorithm, because we have seen that lifting this structure, we precisely get everything that we would have from such a projection. Yeah. And that these quasi-periodic sets or mean quasi-periodic sets are obtained by projections with bounded windows. That's a fairly simple to understand construction. Yeah? So that's really the structure. But that was for the cap tiling. So now we have to get back to the hat, because you might say, okay, now you have shown the cap tiling and you told me, okay, it's all topological conjugate, so the spectrum remains the same, but how does it actually work? And in order to explain that, I have to go back to one dimension and use the Fibonacci chain. And by Fibonacci chain, I do not mean the symbolic system, but I mean the Fibonacci tiling with two types of tiles, namely long and short. Yeah, and that can be described as in the left third of this diagram. So you see the horizontal line in the middle, and you see lots of points. These are the lattice points, the black point. And at each point, we see an interval attached to it that is part red and part blue. And now the rule is, when your horizontal line cuts through any of these pancakes, yeah, or these target lines, then you get a point, and this point is blue if it's the blue part of the line and red otherwise. And if we don't intersect it, then we don't get a point. Yeah. So on the left, you see it starts with red. It's red, blue, blue, red, blue, and then it ends. And now we want to make a shape change. But what's the only shape change in one dimension? We can change the relative size of the two intervals. Yeah, that's the only shape change we can make, and we do it in such a way that the average density of points remains the same. How can we do that in this image? Well, we shear these vertical lines, and that's in the middle third of the diagram. Yeah, so you see the original version still there and the sheared version. And it's important, it's sheared, not rotated. Yeah, and the shearing actually in this case means that if you shear it so much that the intersection lines become the same length, which means I now make a shape change to go from the geometric tiling to the symbolic version, yeah, where all have the same length and it's type A or type B. Then the other lines run actually through, yeah. So that's a specific property of the Fibonacci, but that's not important. And then on the lower, in the right third of the the diagram, you see the effect of it, yeah. And then you see that you still get blue and red points, yeah. You still cut through that. In fact, you get intersections with the very same lines you got at the beginning, as just that the points have moved. And what does this shape change mean? It actually means we take the very same points from the Fibonacci description, model set description, but project them in a different direction. Yeah. So a shape change is a reprojection of the same set of selected points. And that also happens for the hat. And here is what we get from the cap tiling if we reproject it to get the hat. Yeah, and something magical happens. We are back to the original meta tiles. Yeah, that's because we made the shape change back. But the points of the cap tiling, they now fall onto new positions, and they all fall onto vertices of the anti-hat. But that's no contradiction or no problem. It's still fine, because if you know all the anti-hats, by a local rule, you can fill in all the hats. That's unique. And from the colors of the points, you know that the points are on the anti-hats, and then you know where they are. Yeah. So this is now how you describe these characteristic points of the original hat tiling as a reprojection of the cap tiling. And here are actually the two diffraction images. So on the left is the diffraction image of the cap tiling. On the right is the diffraction image of the hat tiling, which must be periodic, because let me go back. The hat tiling, that's, I mean, the colored points here, they live on a lattice. And because they live on a lattice, the diffraction must be lattice periodic, and that's indicated on the right. And now you might raise the question, how on earth can these two diffraction images be related and actually have the same support? And I agree, this is very difficult to see on this image, but if you, which we will soon sort of say show, but we've at the moment we have only done that on in a Mathematica program. If you sort of say change the projection direction slowly from the cap to the hat, you will continuously see the intensities move, but not the positions. Yeah. So you only see some of the peaks. Of course, the real peaks here, they live on a dense set, and the dense set in both images is the same. Yeah. It's just that some big peaks, they get small, and some small peaks get big, and that's how you turn from the cap to the hat tiling. So indeed, the diffraction looks rather different, but the dynamical spectrum, which is the support of that, is actually the same. Yeah, that really comes out. So much for the hat. So maybe I have a few minutes to just show you what happens for the spectre. The spectre has the advantage that you don't need the reflected version. And in fact, if, as using the lower sequence of images, if you do this little deformation and make sure that the spectre can never be matched by an anti-spectre, then this curly version of the spectre is a true geometric monotile. It doesn't need a reflected version. In fact, it can't use it, and it still only admits aperiodic tilings of the plane, though it still has the funny problem that the set of all spectre tilings that are possible, they form two classes, because they are actually spectres. That's whatever orientation you start with, and the same guy in all 6 rotations. And you have shadow spectres that are rotated by 30 degrees. So that means in any spectre tiling, the spectre occurs in 12 orientations, but the tiling space has only 6-fold symmetry. So you have one tiling space where the spectre, that's the guy that's more frequent than the shadow spectre, and actually the frequency ratio is 4 plus root 15 in this case. And you have the other one where the shadow spectre is the more frequent guy, and the original spectre is rarer. Yeah. So in that case, the spectre rule still defines 2 Li classes. But from the geometric point of view, that doesn't matter. The spectre is a perfect monotile. Now you can do the same analysis that I tried to explain before. You can analyze the cohomology group and find that there are no non-trivial, not asymptotically negligible shape changes, and therefore we can do the same analysis again. We can go for the self-similar member in this family, which now has somewhat weird prototiles, 9 of them, in fact, which come out of the combinatory hexagons that were used in the original paper by Smith et al. And you can again make a tiling out of that. So this is the tiling that comes out of the self-similar, as a self-similar inflation tiling, and this is a patch of the tiling. Yeah, so it's rather complicated. And again, you can construct control points. And in fact, if I go back, you will notice that certain tiles always come in pairs, like the dark blue and brownish red one, and also a green one. And that is, you can actually reduce the entire analysis to an object with 5 tiles, where certain pairs only get a control point. So we have 5 types of points, and then you do the same analysis. You look for the translation, the return module. You realize that's the projection of a 4-dimensional lattice. You identify the lattice, you lift the points, and you get this window, which is now fractal everywhere. But the level of the fractal curve is different at different points. So there are certainly a few funny features that deserve further analysis. And that's the end of it. What's the outlook? I mean, coming from dynamical systems, when you know something as pure point, a topological pure point spectrum, you also want to calculate the eigenfunctions, maybe, yeah, and that can be done, even though the windows are rosy fractals. So that actually means we have to do a bit on the harmonic analysis of rosy fractals, and you can ask yourself, how on earth do we calculate the Fourier transform of a rosy fractal? Yeah, exactly. Well, that's possible in this case because there's an inflation picture behind, and you can write that as an iterated function system in the right way and actually calculate it. For those who know Markov partitions, this gives rise to very interesting Markov partitions. What I just said about the rosy fractals actually means that also the Fourier-Borg coefficients, they can be calculated via matrix co-cycles. So there is a very explicit approach to them. Yeah. So that's kind of clear, that can be done and has to be done. And in fact, my PhD student, Jan Masaj, he has done part of it already and is in the process of writing that up. And we got some help from Andrew Mitchell. So he was here for a research visit, and they did quite a bit on that. And now the obvious questions are there other monotiles? So maybe I missed something, but to the best of my knowledge, despite a very intensive computer search, there haven't been any more. And the most pressing issue maybe is, what about 3D? Because after all, we live in 3D, and 3D monotiles, they would be particularly interesting. There are some suggestions, but proving the monotile property is very hard. Why is that? Well, in the plane, the proofs, or the original proof, there's then an alternative one, 2 alternative ones later, but the original proof used an exact enumeration of all finite configurations. And these algorithms, they do not seem to have an easy 3D analog. Again, I might be missing a point there, but I understood from Greg Kaplan that at the moment they don't know how to set up a search algorithm in 3D, even if you have a representative and a candidate, to make sure that you enumerate all the possible surroundings, and then you can't play this meta tile game. Yeah. And then an interesting question is, what about the role of almost periodicity? So far, all monotiles, or things that are very close to monotiles, have turned out to be almost periodic or quasi-periodic in the mean sense, not in the Bohr sense, but in the mean sense. But there is no a priori reason why it should be, though it would be interesting, of course, yeah, if, so to say, a periodicity long-range order would force almost periodicity, that would be a pretty strong statement, yeah. And this brings me back to the initial question: do we actually understand Euclidean space well enough? And I think maybe there are lots of pieces missing, and that's why I believe this is only the beginning. And that's maybe a good point to stop, and thank you for your attention.
Great. Thank you so much, Michael.
Now I can see the chat. I don't know why I couldn't see it earlier. Okay.
Does anyone have any questions? No, if not, thank you very much.